Hi there, so this lesson is on section 6.1, differential equations in slope fields. And we have been studying differential equations for a long time now. Remember that a differential equation is an equation that has one or more derivatives in it. The order of the differential equation is the highest derivative present in the equation. So like if there's a first derivative is the only derivative present in the equation, then it would be a first order differential equation. Or if the highest derivative is the second derivative, then it would be a second order differential equation. But we're not really going to get too much into that at this point. We do know that anti-differentiation, indefinite integration, and solving differential equations all imply the same process, the process of integrating. The differential equations that we have seen so far have been explicit functions of a single variable, where when we're solving these equations, it meant getting back to y equals or f of x equals to some rule that's in terms of x. So here are some differential equations that we have solved so far. So like dy over dx equals to 3x squared. And remember, when you solve that differential equation, you're trying to find the equation y equals, that would be the antiderivative of 3x squared. And then dy over dx equals to cosine, dy over dt equals to cosine of t. Sometimes the independent variable is something other than x. And then dy over dx equals to 3 over 2 minus x. So if we're solving that third equation, you could always give it a try on your own. You could pause right now to make sure we get the same solution. It means that we're integrating. So we're going to integrate 3 over 2 minus x in order to find y. So we would have y is equal to the integral of 3 over 2 minus x dx. And we do have to do a u substitution in order to integrate this. So I'm going to let u equal to 2 minus x. Then du over dx is equal to negative 1. So I can say negative du is equal to dx. And replace that dx with negative du. So now I'll have the negative out here. I could pull out negative 3, because that 3 is still going to be there after doing the u substitution. So I would have negative 3 times the integral of 1 over u du. And then when we integrate, we get negative 3 times the natural log of absolute value of u plus c, right, to represent the infinitely many antiderivatives of 3 over 2 minus x. And then making sure to substitute u back in. There we go. So we are able to say that the solution to this third equation is y equals to negative 3 times natural log of absolute value of 2 minus x plus c. So the solution that we just found, remember, we refer to as the general solution. And we know it's the general solution because of this plus c, right? That plus c represents an arbitrary constant because all of the antiderivatives of 3 over 2 minus x would differ by some constant. Now, if we wanted to find a particular solution, that would mean that we were trying to find c. So we could find the particular solution using what we call an initial condition. And the initial condition in this case for the particular solution that we are going to solve for is that y is equal to 0 and x is equal to 1. So 1 comma 0 is a point on the graph of the particular solution. So dy over dx equals to 3 over 2 minus x would be the derivative of this particular solution. And we are trying to find the original function that passes through the point 1 comma 0. Okay, so in order to solve for c, we are going to replace y with 0 in the general solution and x with 1. Okay, so the left-hand side is 0. Now, 2 minus 1 is 1. Natural log of 1 is 0, right? The log base anything of 1 would be 0. So we just end up with c is equal to 0. So the particular solution to that differential equation with this initial condition would be y equals to negative 3 ln of absolute value of 2 minus x. So this is the graph. This is the equation whose graph would pass through the point 1 comma 0 and also has a derivative of 3 over 2 minus x. Okay, so next we are going to look at verifying that an equation is actually a solution to a differential equation. So we are going to verify that y equals to e to the negative 2x is a solution to the differential equation y prime plus 2y equals to 0. Now y prime represents the derivative, so we do need to determine what y prime would be in this case. So thinking chain rule, derivative of the outside would be e to a power, leave the inside alone, and then times the derivative of the inside would be times negative 2. So that's negative 2e to the negative 2x is y prime. So now in order to verify, it's basically plug and chug. We want to make sure that when we plug in what y is equal to and what y prime is equal to, that the equation makes sense, that the left-hand side equals to the right-hand side. So when we do that, substituting in negative 2e to the negative 2x for y prime, and then e to the negative 2x for y, we think, okay, well, is I equal to 0? And yes, it is. So you could kind of do a mental check, or if you want to simplify that, you would get down to, yes, 0 is equal to 0. Left-hand side equals to the right-hand side. Okay, so then you can try doing the same thing for all of these solutions, so verifying that they are actually a solution to each of the differential equations. So the equation column is the differential equation, and then the solution column on the right is what we're saying is the solution, and then we need to double check that it actually is, and not all of them actually are. So you could pause this for a second and give these a try on your own. See if you could verify which ones are solutions and which ones are not, and then check your answers, and then I'm going to go through them right now. Okay, so in this first differential equation, it looks like we need y prime. So I'm going over to the solution, right, which is the potential solution, and I need to find y prime. So that'll be 3e to the 4x times 4, which can also be written as 12e to the 4x. So then whenever we substitute y prime in, we'll have that on the left-hand side, and then 4 times what y is equal to, which is 3e to the 4x. Oops. And we think, are those equal to each other? Well, you could always simplify, and then you go, yes, those are equal to each other. Verified. Okay, so y equals 3 times e to the 4x power would be a solution to that differential equation. Next one, it looks like in this differential equation we will need a y prime. To find this y prime, we get to practice some of our differentiating skills. So let's use product rule, since x squared times e to the x is a product. So first factor times derivative of the second factor plus the second factor times the derivative of the first. Okay, so now let's plug y prime and y in. So we'll have x times y prime Okay, minus 2 times y. This is also just practicing your algebra skills. And then is that equal to x cubed times e to the x? Let's see. If we distribute this x, then we will get x cubed e to the x plus 2x squared e to the x minus 2x squared e to the x. And yes, it's going to be equal. Right? We could see that because the 2x squared e to the x's, those would cancel, leaving us with x cubed times e to the x on each side. So yes, that is a solution to the differential equation. Moving on to the next one, we need y double prime. So this would be a second order differential equation. So we need y double prime, which means we need y prime first. So y prime would be negative 5e to the negative x, and then minus sine of x. So then y double prime would, it would go back to 5e to the negative x, and then minus cosine of x. So substituting y double prime in, and then minus y, is that equal to 0? Well, no, it's not going to be. You're going to end up with minus 2 cosine of x. Is that equal to 0? Nope. Nope, that's not. Nothing left to cancel. So not a solution. Not a solution to that differential, to the differential equation. Okay, and then the last one, this is kind of foreshadowing a little bit into section 6.2, 6.3. Okay, so y equals to c times e to the 4x, where c is a non-zero real number. Let's see, we need y prime. So c, remember, is just a constant. So we need y prime, let's switch colors here. Let's use orange. Y prime, we would have 4c e to the 4x, because it would be c e to the 4x times 4, finishing chain rule. 4c e to the 4x, and then we have 4 times c e to the 4x. And right away, you can see that those would be equal to each other. So yes, that is y equals c e to the 4x power is a solution to that differential equation. Okay, and then this is slightly different, but we just want to verify that when y equals to c sub 1 plus c sub 2 natural log of x is the general solution. So notice that we have those arbitrary constants in two places, but is the general solution to x times y double prime plus y prime equals to 0. And then, that should say then, we want to find the particular solution. Given that y equals to 0, x equals to 2, and y prime equals to 1/2 when x is equal to 2. Okay, so first let's verify 2 steps here. We need y prime. So derivative of c sub 1 will be 0. Derivative of c sub 2 times natural log of x would be c sub 2 times 1 over x, or c sub 2 over x, which I'm going to rewrite as c sub 2 times x to the negative first in order to find y double prime using power rule. That would be negative c sub 2 x to the negative second power, which is negative c sub 2 over x squared. So then to verify that is the general solution to that differential equation. Plugging in y double prime. And y prime. Is that equal to 0? And that would end up being c sub 2, negative c sub 2 over x plus c sub 2 over x, which that is equal to 0. So yes, that is a solution. That is the general solution. Okay, so the next part of the question, let's go ahead and find the particular solution. So we want y equals where we know what c sub 1 and c sub 2 are. So in order to do this, let's look at what we have. We know that when x is equal to 2, y is equal to 0. There's nowhere that we could plug that in where we'd only have one unknown. Like if we plugged into the original, we still wouldn't know what c sub 1 and c sub 2 are. So then if we look at we do know what y prime is when x is equal to 2. So we can use that first derivative and we could plug 1/2. So I'm using the first derivative. In order to solve for c sub 2. So replacing y prime with 1/2 and 2 with x, I would get c sub 2 is equal to 1. Which then we could plug in the x, the y, and c sub 2 into the original equation, and we would be able, into the general solution, and then we could solve for c sub 1. So we would have 0 equals to c sub 1 plus 1 times natural log of 2. So c sub 1 will end up being equal to negative natural log of 2. So the particular solution with those initial conditions would be y equals to negative natural log of 2, which you could write as natural log of 1/2. Plus c sub 2 is 1, so then just plus natural log of x. And if this were like a multiple choice question, then you might have to, like you might look and go, oh, well, the answer is not there. I don't see y equals to negative natural log of 2 plus natural log of x. So then using log properties, we could rewrite this as natural log of x over 2. And maybe that answer's there. So you might have to use some algebra. But all three of these are the particular solution to that differential equation. Okay, so next up, slope fields. So we've talked about how you can find a general solution to a differential equation or a particular solution. The general solution represents infinitely many possible equations who all have a derivative or second derivative equal to whatever the differential equation is equal to. So sometimes we have seen that when we're solving, we talked about before how when we're solving a differential equation, we use the process of integration. And you guys have seen that you cannot integrate everything. So sometimes solving a differential equation analytically can be impossible. Or very, very difficult, and maybe use techniques that we are not familiar with at this point. However, there is a graphical approach that you can use in order to learn a lot about the solution of a differential equation. Basically, by thinking about finding the slope at any given point and thinking about representing that slope as like a little line segment of the tangent line to a curve. And then once you've graphed all of those little line segments together, they make up a slope field, which would actually show you what the general shape of all of the solutions, the general solution would be to a differential equation. So it gives you a visual representation of the solutions to a differential equation. So I've given you an example here. Now, the little green line segments, those are the actual slope fields. The blue curve, the red curve, and the green curve are actually particular solutions to this differential equation. And this is actually a differential equation that you guys know how to solve, right? Like we could find what y is equal to just by integrating x squared minus x minus 2. You guys know how to integrate that just using power rule for integration. So we would get x cubed over 3 minus x squared over 2 minus 2x plus c, right? That's the general solution. Notice the general solution is a cubic, and c, remember, just represents a conic, not a conic, sorry, I just blanked out for a constant, I don't know why I said conic, a constant, an arbitrary constant. And if you look at the graphs of the particular solutions, don't those look like different cubics, graphs of cubics? So like the blue graph here, notice that it passes through the point 0, 4, which if you plug 0 in for x and y in for 4 in for y, I can think, we would get that c is equal to 4. So the particular solution that passes through 0, 4 has the initial condition x equal to 0, y equals to 4, would be y equals to x cubed over 3 minus x squared over 2 minus 2x plus 4. And the red graph, it looks like, passes through the origin. So that means x equal to 0, y equal to 0 could be thought of as the initial condition there, which means that c would be equal to 0. So x cubed over 3 minus x squared over 2 minus 2x would be the particular solution that would pass through 0, 0. And then the green graph looks like it passes through 0, -4, meaning c would be -4. Okay, so those are three particular solutions to that differential equation, but you could see just looking at the slope field, so those little green line segments, the general shape of all of the possible solutions to that differential equation that are all just shifted up or down, so all differ by a constant c. So in order to sketch a slope field for a given differential equation, you're determining the slope at different points, at different values of x and y. So you can make a table. So if we were trying to sketch this slope field, I'm going to pick kind of a brighter color so that you guys can see my slope field. I would make a table x, y, y prime. Remember, y prime is just the first derivative, represents the slopes of the tangent lines at a point on the curve. Okay, well, notice that in this differential equation, there's no y. So y prime is only dependent on x. So it doesn't matter the value of y, it just matters the value of x. So like we can choose different x values here. So like when x is equal to -2, y prime would be equal to +4. Well, that's a pretty steep slope. Now for reference, when you are sketching slope fields, you know that, like a slope of positive 1 would come out like at a 45-degree angle. A horizontal, or a slope of 0 would be a horizontal line segment, right? A slope of -1 would also, right, have a reference angle of 45 degrees. And then anything like 4 should be way steeper than 1. So you just want to make sure that each use kind of the slopes of 1 and 0, or undefined, right? Vertical would be a vertical line segment would be an undefined slope. Use those kind of as your reference slopes, and then everything else, just make sure like a slope of 4 needs to be steeper. So when x is equal to -2, y prime will be +4. So I'm going to draw some pretty steep slopes. And since I'm on the iPad and Notability, I'm going to use the copy and paste feature here. Okay. And then when x is equal to -1, y prime would be 1. So I want to make sure that when I draw that slope, that line segment, that it looks like that was going towards the point 0, -1, right? Which would, if we were trying to connect those 2 points, then would have this, create a line with a slope of 1. So copy paste, which I realize you cannot do with pencil and paper. Just do the best you can. Okay. And then when x is equal to 0, y prime would be 0. So horizontal tangent lines. And then when x is equal to +1, y prime would be 1. So I could actually just copy and paste from over here. And then when x is equal to 2, y prime ends up being equal to 4. Now this was a very simple slope field. But that's okay to get us going. Oops. Okay, there we go. Okay. And the slope field extends in all directions, on and on and on. Now, looking at the differential equation, y prime equals to x squared, you guys know that if you were to solve that differential equation, its solution, its general solution, would be x cubed over 3 plus c. So you guys can see that the general solution would be cubic, so x cubed vertically compressed by 3, and then that plus c just represents constants. So you could pick particular solutions, like the particular solution that passes through 0, 0 might look something like that. It's a rough sketch. But you could also sketch particular solutions based on a given slope field, and you might be asked to do that in a free response question. So in general, to create a slope field given a differential equation, to every point x, y in the domain of f, assign a small piece of tangent line with a slope of f prime as a function of x and y being equal to dy over dx evaluated at x, y. The slope fields will be made up of all of the small pieces of tangent line, and together will give shape to all the possible solutions to the differential equation. Now, going back to the slope field we just created, like we could have used x equal to 1/2, x equal to -1/2, and we could have had more little line segments, and that just would have made our slope field give us a more accurate picture of what the general solution set to the differential equation would look like. Thing is, you're not going to be asked if you're sketching a slope field, you're not going to be asked to sketch more than like, I feel like 12 points would be a lot to sketch the line segments for the slope field. Maybe like 6, 12, somewhere in there, in that range. Now it can be really helpful to identify trends. So for example, for this differential equation, y prime equals to y minus x, like maybe starting with identifying where y prime would be equal to 0, right? Like where there would be horizontal line segments, horizontal tangent lines. So if we did that, so setting y prime equal to 0, right, we would get when x is equal to y. So that would be like 1, 1, 2, 2, 3, 3, negative 1, negative 1. Or along the line, y equals to x is where we would have horizontal tangent lines. Here, I should make this thicker. Okay, so that can be helpful, a good starting place. You could solve for when y prime is equal to 1 if you wanted to, or negative 1. Or you could you're just trying to spot trends. So like whenever you start filling in your table, so x, this is thick, y, and then y prime. You can spot trends and you won't have to fill in as many points in your table. And then we're going to actually sketch the solution that passes through the point 1, 0. Okay, so going through this, if we let's do like 0, 1. So 1, that would be 1 minus 0 is 1. Okay, make sure that looks like a slope of 1 so that it's aiming up at 1, 2 and down at negative 1, 0. And then if we were to notice if we were to do 1, 2, that would be 2 minus 1 is 1. And negative 1, 0, right? Because 0, negative 1 would be 1. So along this line, which if we had set y prime equal to 1, right, we would have y minus x. So along the line, y equals to x plus 1, we have a slope of 1. You could do the same for like looking for where would be negative 1. So here, I'll do that down here. So negative 1, where this y prime would be equal to negative 1. So just choosing some easy values as points of reference. So that would be for when y is equal to x minus 1. So shifting down 1, that would be a slope of negative 1. It's not quite steep enough there, huh? You get that? That doesn't look so... That's a little better. Okay, and then if we went so slope of negative 1 along x equals to negative 1. Oh, that was silly. This would not be the point. When x equals to negative 1, so right here, so at 1, 0. Maybe I should just copy and paste. Copy, paste. Copy, paste. Copy, paste. Okay. And I mean, you could keep going. You could look for where there's like a slope of 2 or negative 2. But or you could just plug in values. So I'm going to keep plugging in values here. So how about -2, 0? So that would be 0 minus -2, which would be a slope of +2. So it needs to look steeper than a slope of 1. Okay, and then I just have a feeling here. What if we did -1, 1? That would be 1 minus -1, which would also be a slope of 2. And you could always confirm that, and then 0, 2, that would be a slope of 2, right? You could always confirm that by setting y prime equal to 2. And then how about -2, 1? So that would be 1 minus -2. That would be a slope of +3. So that needs to look steeper. And how about -1, 2? That would also be a slope of +3. And -2, 2 would be a slope of +4. So it shouldn't look vertical, but it should look pretty steep. And then 1, -1. So -1 minus 1 would be -2. Okay, and then 0, -2 would also be -2. 2, 0 would also be -2. So then 1, -2, almost done. 1, -2 would be -2 minus 1, that will be -3. And then 2, -1, that would be -1 minus 2, so that'll also be -3. And then 2, -2, that would be -2 minus 2 will be -4. Okay. So then sketching the particular solution that passes through 1, 0, using these as a guide, I think it'll come down kind of like this, and then it comes around, and then is guided by those line segments that are slope of 1. That's what I think it would look like. And you guys do not know how to solve this differential equation. Now, if you want to check with Wolfram Alpha, I think you will see that our solution is pretty good. Pretty good sketch for the solution that passes through 1, 0. Okay, here is a previous free response question that has a slope field in it. Differential equation. Given differential equation, and you're asked to sketch the slope field. At 9 points indicated, sorry, I just spilled some water on here. At the 9 points indicated, okay. So let's see. This one ends up not being super nice. It's actually maybe just the fastest to just make a table. When there's so few points, it might just be fastest to make a table. You just have to look at the given differential equation and decide. Let me make this a little bit skinnier again. So x column, y column, dy over dx. So I'll just go through each of the points, I think. So -1, 2. -1, 2 would end up being 1/2. -1, 1. -1, 1 ends up being -1/2. Okay, and then -1, 0 is -3/2. Instantly looks steeper than 1. Okay, and then how about 0, 0? 0, 0 ends up being -1. Okay, and then extend my table over here. Okay, 0, 1. 0, 1 is 0. How about 0, 2? 0, 2 is 1. 1, 0. 1, 0 would be -1/2. And 1, 1 would be +1/2. And 1, 2. 1, 2 is 3/2. So this is kind of this one is, I think, maybe just easiest to make a table. Go with it. So question B is asking us to find the second derivative in terms of x and y. Make sure you're paying attention to the directions, that you're reading very carefully. So in order to find the second derivative here, this is for question B, our second derivative with respect to x, that would be 1/2 times dy over dx. Not times, plus dy over dx. 1/2 plus dy over dx, which, remember, it says in terms of x and y. Well, we know what dy over dx is in terms of x and y. So we could replace dy over dx with 1/2 x plus y minus 1, and then just combining like terms. We have 1/2 x plus y minus 1/2. Okay, describe the region in the xy plane in which all the solution curves to the differential equation are concave up. Well, concave up would be wherever the second derivative is greater than 0, right? Wherever the second derivative is positive. Concave up looks like a cup. So figuring out where this 1/2 x plus y minus 1/2 is greater than 0 and how we could describe that. Well, that would be when y is strictly greater than -1/2 x plus 1/2. So all the solution curves to the differential equation are concave up on the half plane, described by y strictly greater than -1/2 x plus 1/2. So shading above that line, like if we looked at that line, shading above. So I'm going to write that as all solution curves to the differential equation are concave up where the second derivative is greater than 0, which is on the half plane, right? That the line y equals to negative 1/2 x plus 1/2, that divides the xy plane in half. So on the half plane that's shaded above that line, if you were trying to shade that solution set, which is the half plane where y is strictly greater than negative 1/2 x plus 1/2. So wherever that's true, all the x comma y coordinates where that is true would be where the solution curves would be concave up, look like a cup. Okay, I'm going to add a page here so that we can look at answering the other parts. Oh, I just realized in class we didn't go over these other parts, but that's okay. Now, C, question C. What is question C? Question C says, let f of x be a particular solution to the differential equation with the initial condition f of 0 is equal to 1, right? That represents the point 0, 1 on the graph of f. Does f have a relative minimum, a relative maximum, or neither at x equals to 0? Well, at x equals to 0, well, let's think about what we have, what we know. We do know what dy over dx is. The thing is, dy over dx is in terms of x and y. So doing an analysis line would be tricky. We do, in part B, have the second derivative, though, so we could always use the second derivative test, right? So if 0, 1 is a critical point for f, which would mean that the first derivative would be 0 at 0, 1, or undefined, then we could look at what happens to the second derivative at 0, 1 in order to determine whether that point is a relative minimum, a relative maximum, or if it doesn't tell us anything. So let's see what happens. First off, we need to see whether dy over dx is equal to 0 at that point. So this is at 0, 1. Let's see, dy over dx, it would be 1/2 times 0 plus 0 minus 1. Oh. At 0, 1. Oh, I plugged in. I was like, why shouldn't this work? Sorry, should have plugged 1 in for y. So we do get 0. So that means that 0, 1 is a critical point, which means it is potentially a relative maximum or minimum. So let's see when we evaluate the second derivative at 0, 1, do we get a positive value or a negative value? Or is it undefined? Or 0? And then that would not be helpful. So our second derivative, plugging in, so that would be 1/2 times 0 plus 1 minus 1/2. So we get positive 1/2, which means that critical point lies on an interval where the graph would be concave up, looks like a cup, and means that there would be a relative minimum. F would have a relative minimum at the point 0, 1, because that critical point is on an interval where the graph would be concave up. Okay, so that's how we're going to justify. We're going to say F has a relative minimum at 0, 1 because dy over dx. This was a important part. Had to be a critical point. So because that equals to 0 and the second derivative evaluated at that point was greater than 0. That's our justification. That's how we know there's a relative minimum there. Okay, and then question D. Find all the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. Okay, well, where is all solution to the differential equation? Well, a differential equation has dy over dx in it, so if we wanted to find the derivative, dy over dx of y equals to mx plus b, right? Wouldn't that be dy over dx equals to m? Which if you then were to set in your differential equation, here, let me copy and paste this. Okay, so then if we were to, in our differential equation, would that be helpful to us? If we were to replace y with mx plus b, and then regroup and factor out an x. So that would be 1/2 plus m times x. And then plus, the constant would be b minus 1. Okay. Well, we do have a system here. Like if this is equal to dy over dx and that's equal to dy over dx, you could think of this as being in the form m plus 0 times x, or 0x plus m, right? Which would mean, why is that down there? Which would mean that 1/2 plus m is equal to 0, so m is equal to negative 1/2. And then b minus 1 is equal to m, which if we know that m is equal to negative 1/2, that means that b is equal to positive 1/2. And those are the answers. So m is equal to negative 1/2. And b is equal to positive 1/2. Okay, and then for matching each slope field with its differential equation. So I would my first strategy would be looking for the trends, or looking for like where, so look at a differential equation and be like, okay, well, where do the horizontal tangent lines occur for this differential equation? Like where is y prime equal to 0? For this one, it would be where y is equal to negative x. So along the line, y equals to negative x. So looking which of these graphs along the line y equals to negative x has tick marks that have a slope of 0, and that would be for b. So I and b, and you could go I matches with B, you could go a step further. You could also go, okay, well, where is y prime greater than 0? Where is y prime greater than 0? Or where is y prime less than 0? And then you go, okay, x plus y greater than 0. So when y is greater than negative x, that's where you would have positive sloping tangent lines, and that would be, well, look, that matches with B as well. So above the line, y equals to negative x. So looking for those trends, you could then for 2 be like, okay, well, if we set y prime equal to 0, when x is equal to 0, of the two graphs that are left, notice when x is equal to 0, there are horizontal tangent lines for A. So this is going to be A, match with the graph of A. And then when y prime is equal to 0, y is equal to 0. And looking at that last graph, we can see along y equals to 0 is where the horizontal tangent lines are. So matches with C. Okay, but kind of trying to look for those trends. You could also like pick out if a slope is obvious. Well, remember, it's kind of tough to tell because you're not reading a number. The slope's not telling you what it is. You're kind of, the easy ones to identify are wherever the slope is 0 or is undefined, where there's a vertical tick mark to represent the slope. Those would be the easiest ones to look for, or just positive sloping tangent lines, negative sloping tangent lines, but you're looking for those trends. Okay, this was section 6.1.